Good evening. Oh, there we go. Let's try it again. Here we go. Thanks, Jörg. You know the spiel. Good evening, everybody. Good evening, Davos. Thank you. It's great to see you. It's welcome here into this room and welcome to the live stream joining us from wherever you're joining us. Welcome to what promises to be truly an incredible evening. I'm very excited. Together, we're going to be taking a voyage from literally the building blocks of life to the lungs, the luscious lungs of our planet, then out to near orbit and to far, far, far beyond. It's going to be an incredible journey. My name is Chris Lubkeman, and I have the pleasure and the privilege of being the leader of the Strategic Foresight Hub within the Office of the President of the ETH Zurich. And here in the room, we have some really cool music going on. So for those on live stream, you don't get it, but it's really kind of nice, actually. You can keep going. I think this is the Amazon sounds. And most importantly for tonight, I am your host for this evening. The ETH Zurich has been in Davos, present during the World Economic Forum since 2017. Quite a long time, and we're really glad to be back here again. We've designed our ETH Meets Davos program to provide a forum for scientists and science-driven organizations to engage with the public, with colleagues, to share insights into current topics, discuss grand challenges, and envision our future together. We're in the room of this newly renovated room of the Physical Meteorological Society. No, the Physical, it's a long name. Physical Meteorological Observatory Davos, PMOD. And we're going to hear a lot more about that from the director in just a few minutes. Now, many of us listening to or reading the news or walking through our landscapes have had the feeling that we're confronting massive change to just about every aspect of our lives. Climate change, biodiversity loss, democracy being disputed, excuse me, global pandemics, national governments being unseated, war, technological disruptions present a very clear and present danger to the society which we know and love. More importantly, for us, it also presents us the opportunity to consider, to think, to focus on finding solutions to these challenges, to really think hard about them, to embrace the deeper meaning of our existence, and perhaps to rediscover some overlooked aspects of our lives. This is something which we take very seriously at ETH Zurich with the Rethinking Living program. This campaign invites us all to touch the core meaning of our humanity, our role in the systems of the world around us, and also to foster a greater sense of purpose. And I think the four individuals who we have tonight will really help us touch on this, and I think in a really, for me, an interesting way. Our time together here in this room and online will be about 75 minutes for this portion. Those who are here physically will afterwards be able to enjoy a wonderful flying apéritif. And first, we have the pleasure of hearing our welcome from our president, Joël Mizot. And then we're going to have the introduction to the PMODWRC by its director, Louise Hara. Then I'll introduce our speakers, and then we're going to share a bit more about their work. And then we're going to have a bit of a dialogue, and then you will also be able to ask some questions. And I asked them to be questions. Preferably, you could even write them down so you could read them, but not a half an hour question. Sound good? So in the Zoom age, everyone did this. Sound good, everybody? Yeah, okay, there we go. All right. No hearts, none of this stuff. So let me first welcome up here a person who is a scientist, an avid mountaineer, parent, professor of physics, and the president of ETH Zurich. Joël Mizot, welcome to us.
Thank you, Chris. I've been asked to stick here for the camera, but I can't do that, so I'm sorry. So it's a great pleasure to have you here. Welcome here. I think there is a very diverse community of people here. And I'm very happy to see Michael Skepman, because he knows this place much better than I do. Okay, so why are we here? Last year at the WEF, I think the last day, we had a meeting here with Luis de Jara and the ESA director, the new ESA director. And then we had something in the pipeline. We were just in the process of hiring Thomas Zubochen, the scientific director of NASA. And then I came here. They presented this place that I had never seen. And I said, wow, what a beautiful place. Let's have a meeting. And probably Luis thought it was a joke, right? But I told Jörg, and Jörg, with his team, they just made it. And the location is beautiful. I don't know if there will be an opportunity to look at the instruments that you have. And now, one thing is the location and the purpose. Why, for me, it was really important to have a meeting here with this title, Observation. Why? What are the main topics at the WEF today? This is AI. This is cybersecurity, climate change, of course, and then, of course, wars and how to get peace in this world. And then take AI. Everyone forgets that at the end, if you don't have good signals, good pictures, good data sets, well, the AI is not worth anything. And so somebody must be producing this high quality data. And we have done that since hundreds of years. First, by looking at the sky, trying to understand how our universe is functioning, deriving some laws of physics. And then, so that was the first step to do that. And we continued with that. And I'm personally very interested in detectors because I've built detectors of all my life. Okay? Smaller at the beginning, bigger, and then very big. Okay? And then what happens is you build a detector for a certain purpose, and then you discover something completely different. It happened. I think it happened to everyone. It's called serendipity. And then this is where it gets really, really exciting. If you want to demonstrate that the theory is right, it's a bit boring. If you want to demonstrate that the theory is failing, then you get attention. Okay, and so this is let's say the scientist, the physicist, how we tick, and we will have here beautiful explanation about the James Webb Telescope, I suppose, where Adrian is involved. But now there is something else coming. There are the challenges of our world that I just mentioned. And data is becoming crucial to tackle these challenges. On one side, using satellites data to understand how the climate change is affecting our world. Forests going away. Last week with Michael, we were at an institute where they looked at snow and ice and how the glaciers disappear and what is the consequence for the water, dealing with water in this world, which will be the next big issue that we need to deal with, and so on. So that's one thing. Again, detectors, observation to better understand what's happening. What we don't have anymore is the time to just spend decades developing a detector and trying to understand. There is a sense of urgency, right, that is there. But there is an additional component now. Once we understand what happens, we need to take measure to counter these effects. And here we need monitoring. And that's another observation that we need. And the monitoring is even more difficult because it has to be, for example, really in real time. Okay, and I just want to mention another example of what we are starting to do. In October last year, we signed a MOU, an agreement with FI Vienna, was also, I think, at this time in New York, with UN to tackle the SDGs of UN, to go in conflict regions and to deal with the reports that we get from the peace troops and try to predict a little bit what is happening. And all this, you need, again, science to deal with this, data, AI, and so on, and better data, and always better data. Just want to finish by saying that having high precision data is very Swiss in a sense. And so we have here, I know you are international community, but Switzerland is very famous for doing excellent detectors that never die. And then so you need additional resources to get the data, but that's another story. When I was in my former life, I was director of the Paul Scherrer Institute, and I had this physicist coming to me. He had built a detector for a satellite, and he said, you know, my detector is the last thing that works in this satellite. I said, it's awful. They maintain a satellite just for your detector, right? And so we had to kill the detector at some point. I'm very good at killing experiments. So with this, I want to thank you all again to be here. I'm really looking forward to these discussions, and I'm thanking also Louise to make this possible. It's really great. Thank you so much.
Thank you, Joel. Thank you very much, Joel, very, very much. Now we have another scientist, a lover of mountains, professor of physics, a space enthusiast, which I didn't know until she told me that, and also the director of the PMODWRC, and as I said already, our generous host or Gastgeberin for this evening. So let's welcome Louise up to the stage, so to say.
Thank you. So good evening, everybody, and thank you, Chris, for the introduction. And now our institute will always be known as the Rapping Institute, PMODWRC. So thank you for that. So our institute here was formed in 1907, and people always ask, why here? Why Davos? And it was because the founder, Karl Dorno, he came here with his daughter who had TB. So this was the era of the sanatoria times, and he was a scientist, and he wanted to understand why the atmosphere in these regions were so good for people with respiratory diseases. So he started to develop instruments to understand this, and this is what the institute is founded on, is understanding the irradiance coming in through the atmosphere and what that means. At the same time, there were other institutes formed. So we have a sister institute just that direction, which is an allergy institute. So it was formed at the same time, looking again at the impact on the body of respiratory diseases. Now they work on asthma, on allergies, on COVID as well, etc. So that's a bit of the history of why we're here. We host what's known as the World Radiation Center, that WRC bit. And the two co-leads of the World Radiation Center are in the room. Wolfgang and Julian, you can put your hands up. Thank you. So they run this World Radiation Center, and it hosts the world standard for flux from the sun, the irradiance, and that's a bit like the Paris meter. So we hold it for the world. The world comes with their instruments here to calibrate to ours, and we have traveling instruments that pack their bags and go to other countries, and we calibrate in other countries as well. So we look in different wavelengths. So we measure the total solar radiance. So that's useful for climate models because it's the major input into understanding climate change. And we also, solar energy companies obviously need to understand this accurately as well. We look in ultraviolet. People understand ultraviolet from skin cancers, for example. Infrared is a reflected heat as well. And we look at particles in the atmosphere and how that affects the irradiance coming down. So pollution, if you have a sandstorm, whatever, that impacts you. And also the ozone. So the observations, you need different instruments for different measurements. So you can't get away in life with just measuring one thing. You have to measure different things, and you have to measure them over a long time period. So for us, we hold some of the longest time measurements in the world in these kind of measurements. And that long-term evolution is really important. So long-term studies are key. Scientifically, what we do is then we have a climate modeling group who do very complex physics, chemistry models, and they look at what happens to the Earth's atmosphere in different circumstances. So going back in history, what's happened, and looking in the future, what happens if the governments don't do what they say they'll do, or if geoengineering becomes more of a big thing, or if we have multiple volcanic explosions, etc., modeling different circumstances. We also look at the source of the irradiance as well as our sun, that you didn't see much of today. But our sun is a dynamic star. It has explosions on it that happen on short timescales. And we look at those as well. And this is a good time to observe, for all of you to observe with these. So at the minute we have, the sun is at its height of activity. It has an activity cycle around 11 years or so. And it's getting to its peak. My neighbors are in Norway this week, and they just sent me stunning pictures of the Northern Lights that they saw. So I'm planning your holidays for you. So Northern Lights, good time to do it. Sun's very active, a beautiful thing to see by eye. And also, if you want to see the hidden solar atmosphere, which we do with our spacecraft, you can go to the USA and see a total solar eclipse on the 8th of April. So just bear those in mind, and then you can see the glorious atmosphere. So I mentioned spacecraft there. There's a model above your heads, which won't fall down on you, don't worry. We also, as well as our instruments that are on the ground here. So it is dark now, so you won't see our instrument garden and our instruments by the door, our instruments on the roof. We have instruments all around this building measuring different things, and we have instruments around the world that are monitoring in different countries. But we also have the instruments in space as well. And they're monitoring the irradiance from the sun. They're taking images of the sun and tracking its changes day by day, minute by minute. Our most recent spacecraft that was launched was in 2020 at a European Space Agency mission, Solar Orbiter, which gets in super close to the sun, closer than Mercury, so it's a bit hot there. So the instrument, the front of the spacecraft, reaches 500 degrees. So your phone would be kaput at 35 degrees. So this is a spacecraft that has challenges and is in a nasty environment. That spacecraft gets close to the sun twice a year, and we're planning now for our next encounter in March. And this is super cool. And we also will get slowly out of the ecliptic, and that will allow us to see the poles of the sun for the very, very first time. We have not been able to see the poles before. So this is something that is really unique. It's real polar exploration by observations. So yes, we've got that excitement coming up ahead. So the observations that we do are on lots of different scales. So the whole sun itself, the irradiance from the sun, and the impact that it has on us here on Earth and the Earth's atmosphere in different ways. So I'll just briefly go back to our sister institute that I mentioned, the Asthma Institute. You may think they've got nothing to do with us at all in terms of topic and linking things together. Recently, obviously, climate change has a big impact on human health. So they also want to understand our climate models and the changes in the atmosphere to understand the impact on human health. So observations at all scales are really important. Observing our environment, observing what's happening on Earth, what's happening in the solar system, what's happening in the universe, is important for us to constrain and understand and improve our life, our humanity. So this is where I will then hand over back to Chris, and I look forward to the panel discussion. Enjoy yourselves tonight.
Thank you.
Thank you.
Thank you. Thank you. Thank you so much, Louise. I'm going to ask all of our panelists just to come on up because we're going to get a little tiny bit behind time. We're going to keep rocking here. So we have 4 wonderful humans here for tonight. I'm going to ask each one of you to introduce yourselves instead of me doing it. So Adrian, first, you're up first.
Good evening.
You've been referenced, and they're pointing at this little tiny satellite. And I think you've got a different one that you've worked on.
I don't know if that's a one-to-one model, but yeah, ours is a bit bigger maybe. So the James Webb.
So who are you and where are you? Just very briefly.
Yeah, so I'm a senior astrophysicist at the ETH Zurich in the Institute for Particle and Astrophysics. And I'm focusing, or my research area is in the field of exoplanets. So these are planets orbiting other stars than our sun. And my focus is in instrumentation, meaning building instruments for observations. And one of them a long contribution is a contribution to the James Webb Space Telescope. I'm involved there for 20 years already. Now the mission is flying, as you probably know, and provides great data. And I'm already very busy with the next big thing, which is the extremely large telescope that is a ground-based telescope, being supposed to be the biggest telescope on the planet, 40 meter in diameter. And we developed there an instrument for it, which is then 2 stories high. So this is really a big machine. And last, we want to develop for the future generation, a space mission that ultimately answers the question about life in the universe.
Excellent, thank you. And we're talking about very big things. The next person to your right talks about very little things. Kirsty, who are you and what do you do?
Yeah, so thank you very much. It's a pleasure to be here. I'm Christy Diner. I'm a professor of environmental DNA, which maybe you don't know or haven't heard of. And so my work has more or less transpired over the last 10 years, where we've been developing sensors, if you will, but very simple sensors, to harness DNA that we find in water, soil, air. So we can find all these sequences that every life form sheds into the environment. So we know very well from criminal investigations that, all you are leaving your DNA here. And every life form does this where it lives. And so through the advent of sequencing technologies advancing and many other sort of molecular biology innovation that's happened over the last 30 years has led us to this point that we can, look at these very microscopic, we can't even see them, we can't even use a microscope. We have a new microscope. It's called DNA sequencing, right? And so we can observe all life truly unbiased, right? So all life form, as we know, at least on this planet, is DNA based. And we can talk about viruses if you want, if they're really alive, but
no, we're not going to go there. Let's don't go there. Come on, we're going really off the deep end then. So let's just, so that's good. And you also have an ETH spin-off. You spun off and you've created a little entity just to throw in the pitch for the spin-off part
thank
there,
you very much. Yes, and so actually the innovation over the last few years has been to commercialize some of these ways that we do the analysis, because generating these observation data sets is really important for the future of life on Earth and monitoring. Yeah.
Great. Thank you, Christy. Now, and next to you, we have someone who studies life on Earth, has been studying life on Earth your entire career. Carlos, who are you and what do you do?
Yes, thank you very much. Good evening to all. I'm a climate scientist. I finished my PhD at MIT in 1982, and I did, I think, one very good thing. I decided not to stay in the US. I had 3 job offers. I went back to Brazil, my country. And then I been working for 41 years with the Amazon. I decided to dedicate my career to the Amazon, mostly how the forest interacts with the atmosphere, with the climate systems. I'm not a biologist, but still we did 34 years ago, I was the first scientist to publish a paper in Science showing the risks of a tipping point. At that time, 1990, it was, if deforestation proceeded, then the Amazon might disappear, the Amazon forest. And then I continued for many decades with many, more than 30 PhD master students doing that kind of work, going to the Amazon, making all sorts of measurements, etc., including remote sensing we used in our models. And then, a few years back, we know the Amazon is so close to the tipping point. It's no longer a projection for the future. The Amazon is at the edge of the tipping point. The southern Amazon, the dry season is 4 to 5 weeks lengthier in 40 years. It's losing carbon. So I said, I will not stop, but I will try something else that I had never done. So now, for the last 5 years, I'm working in nature-based solutions, looking solutions for saving the Amazon. So I'm involved in one of the aspects. I've been talking to some of you. ETH is the creation, the Amazon Institute of Technology, something of the quality of ETH in the Amazon. Also, how to develop a new bioeconomy in the Amazon, with the tremendous potential of the biodiversity and also bringing indigenous knowledge. And also in Brazil, we released at COP28 a beautiful project called Arc of Restoration, which is to restore 24 million hectares between now and 2050 of the Amazon forest in the southern Amazon. So that would be what I'm trying to do that. And it's very good to be here to find ways to learn with this beautiful science, but also to find ways to collaborate with all of you to find solutions, nature-based solutions for the Amazon.
That's great. Thank you, Carlos, very much. It's great. And to wrap up our grouping here, we have Magdalena as a geneticist by heritage. And now, okay, well, you can pick your heritage, but who are you?
Thank you. Geneticist by heritage. My genetics training is entirely environmental. But that's another topic. So I'm Magdalena Skipper. I'm editor-in-chief of Nature. And I hope Nature does not need too much of an introduction, but I'll give you a little introduction to the journal. Because, of course, Nature, as in the journal that I lead, evolves like everything else does. So we've been around for 150 some years, and we were born really focusing on the natural sciences. So we would really publish most of the work that was discussed here, much of the work that you do. But over the last, I would say, close to a decade, certainly in the time that I've been in this role, which is just over 5 years now, we've really taken that meaning that Nature is a multidisciplinary journal to heart. So we now publish research which is in the social sciences, in applied sciences. We have ambition to go all the way to engineering. We certainly publish clinical studies as well. And if you ask me, I have appetite for us to consider publishing implementation science, which is interesting because that's close to what you were just talking about. So that's about the journal that I lead, and of course the journal is only possible because of a wonderful team that works on the publication really on a daily basis. And if you like to know what my role is like as editor-in-chief of a journal which publishes science news as well as opinion content as well as original research, I like to think of myself as a conductor of an orchestra. So each of my team members is really an expert in what they do, and I sort of bring them together and hopefully bring out the best in them and a sort of a synergy. And indeed, as you say, I sort of was born professionally, if you like, as a geneticist, and then I switched to being a scientific editor. Pleasure to be here.
It's great to have you here. And let us welcome our panel here up. You can hear, it's a fantastic group. And I'm glad I was entirely wrong with that. That was good to know. So I want to stay with you for a moment. So observation, it's an interesting word, and thinking, over time, and Joe was talking about looking up at the sky. From your standpoint in nature, what does that word evoke for you?
An interesting question. So in some way, first of all, when I think about observation, I think about different scales, which was actually very beautifully demonstrated by the panel here. It can be scale from the microscopic or submicroscopic through to very large, but it can be a time scale issue. So of course, observations can be of a moment or longitudinal, cumulative. What's also important to remember, for me, certainly, I'm very aware of it, that when you're talking about observation, there is an observer. And I'm not talking about a quantum effect here. What I'm talking about is that an observer, by definition, implies a point of view. So when I consider observation, I want to think about, or I want us all to consider different perspectives from which something is observed. I'm talking about diversity of perspectives, diversity of viewpoints. From the perspective of actually your diversity here, I'm looking at all of you. You are all different. You have different backgrounds. You will ask different questions. You will also address those questions in a different way. And in order to do that, you will go about observation differently, even if you use the same tools to observe and you work in the same disciplines. So there are many different aspects to observation.
Thank you for that. I'm going to go on the other end. So looking out to the great all, what's observation for you? And I may have a follow-up question for you after that too.
Well, observation is I would say, the only thing we have to actually create evidence and probe what we want to understand with our theories. Quite different to many other science fields, astronomy has not the capability to build experiments. So we base our knowledge on observations only. And just because the scales have been mentioned, astronomy, I think, is interesting because it's not only about the big scales, but it's really, we probe the full scales in time and in space, because what we finally see are quantum effects. We measured it with quantum effects, and yet in between there is the big cosmos. So it's really the macro and microcosmos that is combined in the field of astronomy, and the observations we do really entangle the full range.
Stay with that for just a minute. So when I mean, 20 years on one platform, that's a long time.
It is, yes. It takes some breath.
Yeah. So and
luck.
And luck, but and it's incredibly successful. It seems like every week or every 2 weeks we see something new. But now, when you were working on that, there are things which you expected and things you didn't expect, or maybe you didn't know what not to expect. So tell us a little bit about the relationship between the expected and unexpected.
Well, you sell such a mission, of course, with a specific science case. In the case of James Webb, there were 4 major science areas that were put in white papers and explained why such a mission is needed in order to make progress in the field. However, you never build such a mission just with that expectation, because then you would be rather quickly satisfied. So actually you build this mission for the unexpected and the surprises that come along with the observations. And as far as we are in the mission, we already got many of these surprises, and probably many more will come. So this was always the thing we were looking forward. Also, clearly the big science questions that were underlying the mission are also addressed extremely successfully and beyond that. Yeah.
Absolutely, they're stunning. And so, and also with Christy, similar, because I know in talking with you over the past months, you were surprised by what you found.
Yeah.
You were looking for something, but you found something else. So tell us a little bit about what the tool is exactly, and then what you found and what you didn't find.
Yeah, and so when we think about how we observe life on this planet, we've used mostly sensors that humans have. We use our eyes, we use our ears. And so what molecular biology has opened up is a completely new sensor to observe life. And being able to measure that accurately for the first time when we think about an environmental sample is really surprising, because we can observe how many birds there are, and we've counted things, and we have kind of a discovery rate where we say, okay, based on how we've discovered life, there's an estimate of how many species are on our planet. The sort of robust one, or the one that's sort of, let's say, the conservative estimate is 8 million. The upper estimate is over 1 trillion. Right? That's a pretty big variance. And so what's super powerful about the technology of environmental DNA is we get these samples, and we know that we're sort of uniquely measuring a sequence that's representative of a life form. And when we can take the best knowledge that we have to put a name on that, we're getting it like 15%.
So 15, not 50.
Yeah, 15,
15.
or even less, depending on where we are in the world and what kind of knowledge bank we've built up to identify our sequences from. So there's that huge expanse of life that we're able to measure now, and we don't really know what it is, right? So some of this stuff we can't even put phyla. We don't even know maybe the domain. Like, we're really at this stage of observing for the very first time, all of life. And so I'm super fascinated about what that signal means, and if it's a way that if we were to sample all over the world very well, oversample the Earth with eDNA, would we actually get a better accurate representation of how many life forms we share our planet with, and where are we in that sort of bracketed estimates that we have today? So
It's quite astounding, actually, when you say we only really know what 15% of a certain place is.
yeah.
And and Carlos, you, as you already described, you've been observing the Amazon for quite a long time, and the life in the Amazon as it's evolving. When you see this, you said these two individuals, how do you see your your role of observation, your typologies of observation which you've used and you're using as the Amazon is evolving?
Yes, we are, what Christy said is very important, because really environmental DNA will be something for the Amazon very new. What we do is mostly using advanced remote sensing, but just to look at deforestation, degradation. So we measure very well, globally speaking, but in the Amazon, carbon emissions, carbon removals, those things. The satellite remote sensing system are becoming very advanced. So they are very good in that sense, because you know exactly what's going on. 12% of global emissions are land use change, mostly in the tropics. So that advancement is very important. And also becoming, for instance, as you know, European Union was responsible for reduction of deforestation in Indonesia, because advanced remote sensing was showing the main driver of deforestation. Indonesia, very high deforestation rates, palm oil. So European Union said no more imports of palm oil with deforestation. So this advanced remote sensing, the same, and I hope now with the new legal framework in Europe, do not import anything from the Amazon associated with deforestation globally. So I think this is very important. It's becoming really very important. We are measuring very well also degradation, and also, as I mentioned, we are involved in a large-scale restoration in the Amazon. So we are going to use advanced remote sensing to count the removal, carbon dioxide removal, because that has a tremendous potential in the carbon credits, tens of billions of dollars per year. So I would say in that sense. But the big challenge I would like to place for the science of environmental DNA is the following. It's a big mystery why there was never an epidemic and pandemic originated in the Amazon. All the elements are there. Known thousands and thousands of species of virus, coronavirus, hantavirus, rhinovirus, all. Zoonosis. There is one virus, hantavirus, on a bat. So, the biological science knows very well the origin of all the epidemics and pandemics. Why the Amazon never generated? So I think, environmental DNA is very important. And also, as important, as Christy was saying, what's the potential for a much better economy, a sustainable, we call a bioeconomy, based on the biodiversity, in all the planet, but particularly the tropical forests. We do not have any economic and social value as yet. So environmental DNA, not only explaining these issues related to epidemics and pandemics, but also tapping into the tremendous potential of biodiversity for preserving all tropical forests. And I would say that's what we are trying to do in the Amazon.
So the science of observation, when you I'm just going to come back to this again, but you're looking for something and you find something else. Tell us a story, all of you, about you're looking for one thing and you found something else. Go.
Can I just want
Or
to
you can
offer...
respond. You can do anything you want.
Oh, great.
Yeah.
Now
You can do anything
we're
you
talking.
want. Yeah.
Can I offer a suggestion as an answer to your question? You need a critical host population density for a pandemic or epidemic to happen. I'm assuming you were referring to human pandemics and epidemics.
Yes.
Human populations are obviously very distributed in the Amazon. That could be a suggestion where to start with your question. Okay, I'll get back in line now.
Oh no, you're right at the front of the line.
Oh dear.
Now you get to tell a story about you were looking for something, but you found something. You're observing one thing. This is about rethinking observation. You know, what does it mean to observe? Or you were looking for one thing, but you found something else. Just tell us a story in your career, either as a scientist or as an editor.
So, I mean, first of all, I think when we think about observation, I don't think it's helpful to define it that we're looking for something. I think observation doesn't have to be that directional or that intentional.
Fair.
So yes, it often happens. You heard these stories already, right? Then almost, I think probably each one of you, and many of you in the audience were thinking about this, that you thought you were pursuing a question. I think, Joel, you referred to it at the beginning in your introduction as well. You thought you were pursuing a question, and actually you noticed something else that is really interesting. And of course, in the context of doing research science, which is funded for a specific purpose, that may cause a problem because you want to pursue a different question, and yet you are obliged towards your funders to deliver an answer for which they funded you. But I'm being a little bit flippant.
Not
I think
really.
every researcher, every scientist has that experience that you begin your observation, your exploration. That's another thing which is very clear what was discussed here. I think maybe exploration in this context, less intentional, more free, more open-minded, is perhaps a better word to describe it, where I think about observation. But you know, I wanted to come back to this idea of an observer and how the observer will then sort of determine of what is observed or what is noticed, right? Because of course we are seeing many things, and we're going to zoom in and focus on something. I just want to share an anecdote with you of something actually that happened earlier today in Davos here. I was talking to someone. It was a fairly serendipitous conversation, and that's of course what Davos is very good at. And this person was telling me about their work, his work, I should say, because the gender is critical here. His work about in the context of climate change, and it was very action-oriented work. And he said, you know, from the work and the research and indeed observations, data collection that I and my colleagues have carried out, there were some really surprising directions that came out of it. One of them was that to address ongoing climate change, or should I really say climate crisis, one should engage women. And he said, now, that's a really surprising result. And I was looking at him, and I thought, that's not surprising to me at all. And so that's actually was a lovely demonstration of how the observer can determine what is observed, even though the possibility in the observed data is much, much greater.
Interesting. So thank you for sharing the anecdote. It's a disturbing one at the same time.
Well, it's
Frankly.
educational one,
Yeah,
I think.
okay, educational. Yeah, we can learn from that. So any other comments on the question which I'm not allowed to ask anymore, which was the serendipity, or what you found something which you really didn't know you were looking for? Because you've been doing this for quite a long time. You have to have just a story.
Try to not to answer completely your question, but just to
That's
say
fair.
how important good observations are. Because most of my career I was working on models, climate models, global climate models, local climate models. And just to give you very briefly 2 examples, I was at IPCC fourth assessment report 2007, and at that assessment report was just looking at the science at that time, saying the Arctic Ocean sea ice would disappear by 2100. And then observations were showing it was, melting much more rapidly. So that made the science advance a lot to really now make a much better prediction. So what 1.5 or 2 degrees warming by 2050, the ice would completely disappear during the peak of the summer. So the same for the Amazon. we are doing a lot of work in which we would say global warming, deforestation would really turn the tipping point by 2100. Then observations were showing all southern Amazon degrading very fast. So now we improved the model. So observations, I'm not going to say they are perfect, but they are really in ways much better than only modeling of the climate system.
Because I know you talked also about just sort of this being on the ground observation, because with the modeling, the more activation of citizens in the observation as well. This is what we were talking about a little bit a month ago, and how important that's how important that's becoming, is that citizen science part of confirming some of the models and in the savannification. And this was
Yes, for sure. I mean, a lot of these observations, although they are scientific observations, for the Amazon, they were remote sensing, but also there's a lot of local observations showing what's going on in the Amazon.
Right. So I want you to tell us a little bit more about this extra large platform in Chile that which you're building and what you're hoping to observe.
Well, I mean, going from a 10-meter dish to a 40-meter dish means just you increase your spatial resolution by 4 times and your collective area by the square of it. So it will just be like you had unsharp eyes, and then you correct for them and you will see the universe for the first time sharp. I mean, James Webb already did that in the infrared very nicely, but since we have so good adaptive optics nowadays, ground-based astronomy really can compete with space observatory, with the exception in infrared and sensitivity issues. But otherwise, clearly from the ELT, we will just make breathtaking discoveries to a level of detail that we are currently just blind. One example that we try always to make is with the instrument we are building, if and only if we are lucky that the closest star to us, Alpha Centauri, has an Earth-like planet orbiting in the right distance. With that, we could see it, just that star. But that would be already a significant step, wouldn't it? But we don't know yet if there is a planet, and we're not building this telescope for this purpose. But this is one of the things that, you never know what you discover. But clearly, just getting an increase in spatial resolution will just, as we see it with the James Webb right now, just revolutionize the field.
It's really been mind-boggling for me personally. I just changed my whole understanding of space.
I mean, these are the big steps we do as humankind. These are not incremental experiments, yet another observatory. This is really a generation thing, like the James Webb is. The ELT will be as well, and then hopefully the next mission that we are focusing on right now at ETH also hopefully will bring those big steps.
So when would you anticipate it being operational?
Well, this is now politically dangerous to say a date, but 28 is the first lights at the moment predicted for the telescope. Our instrument will be on the telescope a year later or two. That's currently the
So by
official.
2030, we should be expecting hopefully to be able to see some really cool
Just
things.
imagine this will be a technologically very complicated machine, and I would expect some time to smooth it in, if you like, because there are 800 segments that make this huge mirror together. They have
800.
800, and they have all to be co-phased to the level of nanometers, and that in a turbulent environment where you have also structurally a lot of complicated problems to solve. So this will take some time until the performance most likely will be at the performance limits we expect from it. But 28 is first light, whatever that means. Yeah.
Okay, that's really fantastic. Christy, you were looking like you wanted to add something before, and I kind of went by you. Did I misread your face?
I mean, I had an anecdote I could tell, but I
Please.
also could talk about the future I see for eDNA as well, like what we can do with this technology.
Because
So
my follow-on question anyway. So give me the anecdote, and you can do the future.
So something that was fascinating when we first started taking these samples, and we get a water sample and we look at what's in there. Water's this medium that's moving, right, through a landscape and a river. You can think about, okay, well, does the sample I take here actually measure the life forms that are living in this particular area? And so sure enough, yes, the DNA we find there represents that. But the unexpected thing was how much DNA we found that we couldn't explain from that location. And so a lot of people started getting worried, oh, we're not going to be able to use this technology to look at what's living in a place. And so the change in thinking about that was, well, we can't use it to, like, say, this particular point location, but how do we flip that and then take that information? Like, how do we use something which we've never been able to do, which is a single observation at a point that actually is integrating over an amazing amount of space, potentially. And so some of the first discoveries of how far DNA is actually moving from its source was really transformational in thinking about where we can go with that. And so that's actually some of the research that I'm doing, and one of the big ways that we're sort of involving participatory science and getting anybody, like, so it's wonderful to have these amazing telescopes, but you can't actually put them in the hands of anyone, right? And
Some maybe.
I mean, everyone can go look at it, probably. But what's really exciting about eDNA is that we can actually put these simple instruments in the hand of anybody, and they can go make the observation. So the technical pieces and stuff we do in a laboratory, and we have, you know, sort of the generation of the data, but the observation is the person taking that sample. And on International Day of Biodiversity, which is May 22nd, a UN day to celebrate biodiversity, we are having people who've signed up all over the world that are going to go take a sample from a lake. And this is the hypothesis that my group is testing, that lakes are actually these biodiversity like hotspots where they're accumulating a lot of information about all the species living on in the entire catchment, so all the water that flows into there. And you might think, okay, well, what is that really beneficial? And it actually is 25% of the land mass of Earth is in a lake watershed. So if we can go to these there's 1.4 million lakes, so about 700,000, because there's 1 million of them in Canada. We don't have to go to all the ones in Canada. We could probably get a pretty good observation mechanism to observe the pulse of our planet. And that is unfathomable that we would have such a scalable technology. And it's with people. It involves individuals, my kids, your parents, anybody could go out and participate in generating that observation. And so that's a pretty fun time and a pretty amazing technology.
That's really great. Very cool. I'd like to participate on that with you.
Yeah, you can sign. Well, we closed the survey, but you can still sign up if you know me.
Does anybody in the room have a question which they'd like to pose to our panel? We have one here. Is there anyone else? I'd like to have 2 or 3. There's 1, 2. No, you guys are sitting next to each other. You can't both have a question in a zone. Have one on this side. Yeah, okay. No, go ahead. Yeah. No, you get it first.
Does it work?
Yeah. Yep.
It does work. Hi. Especially to Carlos, but maybe to everybody. I'm not a scientific person at all. I'm a curious entrepreneur. How much does a government, and I'm thinking of your last government, can slow down or even prevent developments like what you are doing at the Amazon, or can speed it up? I mean, how important is politics, governments, funding?
Oh boy, this is a very tough question.
Wait, we should have a glass of wine in his hand for this one. I think.
All of us, particularly climate science, but all of us, we are so concerned with the growth of populism in the political world. Populism from extreme far right and far left as well. So what happens if we continue electing climate deniers, anti-science presidents in many countries? I'm a scientist, can say, US as well. I'm not a politician. If that guy is reelected this year, Argentina elect anti-science president. Brazil had an anti-science president. Deforestation increased like crazy. Emissions, assassination of indigenous people. So I'm just saying, your question is very tough. I mean, what to do about that? Because in democracy, people are electing. So this is a very, very tough question. And of course, in Brazil, during the 4 years of previous president, the science, the remote sensing was showing all those things. The president did not do anything. to respond to that. So is it possible to change people in democracies to elect much better politicians? I would say this is a tough question.
And an important one. Something we're all thinking quite a lot about is how we get, and I see Joel wants to.
Yes.
Yes, you do. Go ahead.
Just want to tell an anecdote that it's not something new, right?
No.
There have been, and during
Great.
McCarthyism in U.S.
There we go. Because then online can't hear you unless you have a
Yes.
mic. Yeah.
I'm on? Yes. So in the 60s, there was this director of the Fermilab in the US who wanted to launch a new accelerator. And he had this hearing, and you had all these anti-science politicians asking him very tough questions. And then came one, what would that do for the defense of US? And then he had this brilliant answer. He said, well, what we do is what makes humanity and US worth to be defended. And I think we can talk about science this way, but also culture. You know, what happens in some countries where cultures is just put down and so on. So we need this kind of reactions, this kind of bright people to answer.
If I may add, I'm constantly expanding us beyond observation. I know the focus here is on observation, but of course observation does not happen in isolation.
No, that's
So
good.
your question made me think about the kinds of constraints that you were asking about can, of course, influence interpretation of what is observed, which can be very dangerous, right? If interpretation is not is indeed affected.
Comes to exactly. Yeah. So, any other comments on this, or we had another question? Daniel has a question. We go right here. Anyone who else has a question? We could probably have one or two more. There's one over here. Daniel, go ahead, and then
Hello.
okay,
thank you
final
very
question.
much,
We're going to wrap it.
to be here. Thank you. It's a privilege. I would like to ask again, sorry, Carlos, on your work and maybe also to the lady who does environmental DNA and how these two things are linked. I mean, Carlos, you mentioned that you have new sort of natural methods to solve some of the Amazon depletion or restoration, regeneration, and whether you could a little bit expand on that, whether they're new. You mentioned also art at some point, or did I misinterpret that?
Arc of restoration. Arc.
Arc.
Okay, okay.
An arc.
But
Okay.
what are the new methods or the natural methods, and how could the findings of our colleague from environmental DNA help you, or how is there a connection? Thank you.
Okay. Go ahead.
Let me start because she has the most challenging answer. Yes, I mean, nature-based solutions that we're looking for in the Amazon, the science panel for the Amazon is like IPCC that was created 2019. We produce some basic measures or messages. One is zero deforestation, degradation, wildfires. Fortunately, 2023, 55% reduction in all Amazonian countries, 50% in Brazil, also reduction of deforestation. Very tough to combat organized crime. It's exploded in the Amazon, all related to cocaine, drug trafficking. So it's nothing easy, but at least we are moving. And then nature-based solutions. One, as I mentioned, Brazil created this arc of restoration, large-scale forest restoration. Of course, reforestation, a large area, but also natural regeneration in large areas. The forest, tropical forests grow very fast, very efficient, although they don't maintain the same biodiversity. But anyway, but the big challenge would be really the other nature-based solutions, how to create all across the tropics, but particularly in the Amazon, this what we call a new bioeconomy of standing forests, valuing the biodiversity. So science has to do a lot about that. DNA, what's the value of DNA in the Amazon? Zero. So, but I think, the potential is there, but we have, of course, indigenous people for thousands of years, they've been using that. But now, with our modern science, we have to show the power of this, the genome sequencing, all this, what Chris is doing, many thousands of good scientists are doing, but we have to bring that to bear with this new bioeconomy for tropical forests.
Here, here. Do you want to add?
Just
You don't have
shortly,
shortly.
I mean, when you talk about nature-based solutions, you have to ask what is a solution for? And so climate is an obvious one when we talk about biomass of plants absorbing and pulling that CO2 out of air. But what is enlightening about making observations of what life forms are there and what genomes and what life has solved to be able to live in that place, in that environment, and how we can harness the power of that to transform, many things we already know, like we have Velcro and we have pharmaceuticals and we have all these amazing things that we can then, sort of harness for our own purpose or for other species or humanity. And so I think, if we lose it, that's the challenge. And so you can't value what you don't measure. And we talk about a lot of these things, but that's the link. So
Thank you, Christy. Thanks. So I've just saw the time. I'm afraid we're not going to get to your question. I apologize. You can ask it in the apero afterwards. But any last statement, last word, last homework? We are ETH, academic institution. You want to give us homework? Any thoughts? Something to read? Any last ones? Go ahead, Carlos.
No, I just want to make a proposal. In 1990s, we created the largest scale biosphere atmosphere experiment in the Amazon called LBA experiment. We put together a large number of scientists, 450 scientists from Amazonian countries, from US, from 5 European countries, and we produced the best science of the Amazon for decades. 2024, we are starting to negotiate with NASA, also European countries, institutions, and to come and to do the second experiment. So we want to bring hundreds and hundreds of scientists. The first experiment, we formed 2,000 masters and PhDs from 1999 to the present. And this new experiment, we also have much more power for understanding this biodiversity, all those things. I'm just saying, ETH and all of you are already invited to join us for this big experiment for the Amazon.
That's great. Thank you, Carlos, very much. I think you'll find quite a few people be interested in this. Any last words? I'm looking one. Go ahead.
Sure.
Yeah, go.
So I'm going to finish as I started by going a little bit beyond observation, because of course nothing happens in isolation, in a vacuum. There is a sort of an ecosystem, and I already talked about moving beyond observation towards exploration, and of course we talked about measurements, and there is experimentation from which there is observation as well. But very little of this is of any value if it's not shared and communicated.
Great point.
And of course, that's what we've been doing here exactly just now. And you do it in your research practice, sharing that information and communicating, of course, to different audiences at different level. So a rather obvious point, but just thinking about the sort of
really great.
The ecosystem of that observation.
That's a really great point. Not underestimate the power of effective communication.
Yeah.
And your journal does that very well, so we can learn from it. And a piece of homework from the two of you?
Well, yeah, maybe from my side, I think you could ask, what does astronomy for the climate, what does astronomy for our planet? And I think it has actually a meaning also. We are extroverted to some extent, but I think it's really by understanding the universe better and by understanding the relationships between planets and stars better, we realize the place of our home as being so unique. So I think, although at some point I'm convinced that we will find life outside of the solar system, I think looking also backwards and see where is our place and how unique our home planet is, I think in some respects the bigger picture also helps the smaller planet-size problems. Also, they are very big for us, of course.
Really great point. Really great point. Anything? Short.
Yeah,
really short.
Yeah, really short. Just that I think we're in a phase of science where you think about the scientific method, and we talk about different stages, and you highlighted these. You know, you observe, you make hypotheses, you experiment, you build a body of knowledge, and then we've advanced, right? And what I find right now in our fourth industrial revolution is we have new powers of observation that are so amazing. And it's fun to be this time as a scientist because we get to sit back and just like be in awe of what we can observe, and then like what are the hypotheses we're going to make going forward when we have crazy fast computers that can take your stuff and my stuff and put it together, and AI that can do all that. This is a really wonderful time to be a scientist and observe, I would say.
That is a perfect way to come to a conclusion for this evening, truly. And Irene, how could we not love to be a scientist today? And I think this is what the message here comes across. It's been an amazing journey for me. I've enjoyed it tremendously, and hope for you as well. And I'd like to thank all of you here in the room and for all of you online for choosing to be with us today. We all have many things to do, especially this week, and I know many of you have taken a long trip to get here, but we do truly appreciate it, and we thank you for that. And before we take time for mingling, continuing discussion, networking, enjoy the exquisite, exclusive culinary treats. Ooh, that was hard to say. From our Taste Lab, the ETH spin-off Taste Lab favorite crew, I'd like for all of us to share our appreciation for the panel and their wisdom and passion. So with that, there is just two things for me to tell you. Still, the apéro continues until 20:30, and you will hear a gong. And a gong means that the shuttle is getting ready to depart. There'll be 2 shuttles officially. If they get full, they keep going. We're going to keep running back and forth, back down to the train station. But the gong and don't everyone run on the first one, okay? That's not cool, right? Stay, hang out, and please mingle and enjoy. And thank you very, very much, all of you, for being here, and for the great team who put it together. Okay. Thank you. Well done.